Now let me say something about standards. There is an organization called ASTM, American Society for Testing and Materials. Okay, ASTM. And ASTM is a very important organization because it gets together to develop standards. And a standard is a procedure that can be followed anywhere else. It can be followed in Spain, in the US, in China, in India, in Mexico. And if you follow the procedure according to the procedure, you're going to get the same value, whether you're in Spain or in the US. So standards are very important. And there used to be a standard called D3379, and that standard had been written to test the strength and the modulus of single fibers. Okay? And what I'm going to show you is that we became very active in ASTM, and we showed that this standard was wrong. And we actually convinced the community. We ended up writing a new standard, C1557, that replaced this, and I'm going to show you why, and I hope you will appreciate the importance of this. We'll talk about data analysis, fractography. So if you go to a book of standards, in the old days, this came in books. Nowadays, you can go to the web and you can find these electronic versions. But when they first came out, this is what the standard looks like. The title was Standard Test Method to Test the Tensile Strength in Young's Modules for High Modulus Single Filament Materials. Okay? D3379. This is the year where it was first drafted in 1975, had been reapproved in 1989. And if you read the standard, it said that it applied to fibers that had a more or less circular cross-sectional area. Okay? And if you take a composite material, let's say a silicon carbide fiber in a silicon carbide matrix composite, this is what we are going to find. You're going to find fibers. You see this dark region here? This is a coating. Okay? And we apply this coating to reduce the strength of the bonding between the fibers and the matrix. Remember that in ceramic matrix composites, we want weak interfaces, okay? And we can achieve weak interfaces by putting this coating around the fibers. These coatings are usually made out of graphite, carbon. You remember how I told you about the basal planes? They're so weak. Well, that's exactly what we have with these coatings. These coatings are carbonaceous in nature, and therefore they are very weak in shear. And these fibers are silicon carbide. The matrix is silicon carbide. But look at the distribution of sizes. You have small diameter fibers. You have large diameter fibers, mid-sized diameter fibers. So you have a distribution of sizes in the fibers. And if you look at the distribution of sizes, you're going to find that you can use the normal distribution to describe how the diameters of these fibers are distributed. And we talked about the normal distribution earlier this morning. So the old standard told you, calculate the area, okay? Calculate the area of a typical fiber. So what they said is, grab a bundle of fibers, put them in epoxy, polish them, put them under the microscope, measure the area of a few fibers, and then divide it by the number of fibers. And that's going to give you the average area of the fibers, okay? And then they told you, test the fiber, and then divide the force needed to break that fiber by this average value of the area. That was the standard. Whether you have a very narrow distribution of fiber diameters or a broad distribution of fiber diameters didn't matter. It told you, grab some fibers, go to the microscope, measure the areas, get the average value, and then every time you break a fiber, you divide the force by this value of area, okay? And that was the standard. It was very simple. You had microscopes, epoxy, you could polish the samples, you could calculate the strength of the fibers. And that was the standard, D3379. And then we asked the question, is there a problem with this approach? Okay, that was the question that we asked. So every time you do research, you have to follow the scientific method. And the first thing you do is you postulate a hypothesis, okay? So the hypothesis here is we believe that the approach used to calculate the strength of the fiber is wrong. That's our hypothesis, okay? So when you do research, you postulate your hypothesis, and then you do a series of experiments to prove or disprove your hypothesis, okay? So that was the approach that we follow, and we said we believe that that's wrong. And we set on and proved that that was really the case. So this is what we did. We said, OK, let's consider that we have a collection of fibers. OK? And let's assume that the strength of the fibers are distributed according to a wobble distribution. So we have talked about wobble distribution. So we said the wobble distribution is going to describe how the strength of these fibers are distributed. This is the wobble modulus. This is the characteristic strength. This is the probability of failure. So the probability of failure is going to be given by this expression. Because of the weakest link theory, we know that the strength depends on volume. So here we have normalized volume by some standard characteristic volume for the material. OK? So that's the first assumption that we make. The second assumption that we make is that, OK, we're going to assume that the diameters are distributed according to a normal distribution. OK? And we can prove it. We can get 100 fibers, look at their diameters, and then plot. And we're going to find that really the distribution of diameters is almost a normal distribution. So this is the expression that we have for a normal distribution. This is the Gaussian function that we discussed this morning. And we are assuming that we know these values. And strictly speaking, we don't know those values, but we know the estimate of those values. Remember the first exercise we did this morning about the CDC? I mean, unless we test every fiber, we will never know the exact values, but we can have very good estimates of these values. So we know the estimates of these values with very high precision, with high confidence, the wobble modulus, the characteristic strength, and also the mean diameter and the standard deviation of the diameter. So strictly speaking, we gotta say that we have very good confidence that we know what the estimates of these parameters of the distributions are. Now we're gonna define something called the modified fiber strength. And this modified fiber strength is gonna be defined by this, where this is the breaking load for the ETH fiber, and this is the average of the cross-sectional areas. So this modified fiber strength is really what the old standard said. You know, take the force that takes to break the fiber and divide it by the average cross-sectional area of all the fibers. Okay? This is what we used to do with D3349-79. And then we did something called a Monte Carlo simulation. So in a Monte Carlo simulation, you want to do a simulation with many outcomes. And the process is very simple. We generate a random number. And from that random number, we can calculate a diameter. Okay? And from that diameter, we can calculate an area. Okay? And then we also generate another random number. And from that random number, we can calculate strength. Now, this is the cumulative distribution function for the diameters. And this is what? The cumulative distribution function for the strength. So this is the cumulative distribution function for the wobble distribution. This is the cumulative distribution function for the Gaussian distribution. So this is for diameters. This is for strength. So generate a random number. That's your probability. You find the strength. Okay? Random number, get your probability, get the diameter. From the diameter, you calculate the area. From the strength, you calculate this breaking load. Okay? And then from this area and this load, from this area and this strength, you get the breaking load. And then from the breaking load, you divide it by the average cross-sectional area, and that gives you your modified tensile strength. Okay? So this is the strength that we will have calculated by following the old D3379 standard. And we can repeat this process 100 times, 1,000 times, a Monte Carlo simulation. So it's just a matter of getting the computer running. And we can do this many, many, many times. And then we calculate something called the estimator, okay? And I'm going to show you here in a minute how we find these estimators for wobble distributions. What we have to do is once we calculate all these strengths, we rank them from the smallest one to the biggest one and calculate this probability according to this formula. And then for the simulation, we assume certain values. We kept the characteristic strength constant. We kept the average diameter constant. And we repeated this process 1,000 times. Okay? We use values of wobble modulus of 3, 5, 10, and 15. standard deviations for the diameter of 1, 2, 3, 4, 5 microns. And for each combination, we did this 10 times, okay? And we just let the computer run there for a few minutes. So this is what we have. So if we assume that we have a standard deviation of 1 micron, this is what the distribution looks like. Standard deviation of 2 microns, 3 microns, 4 microns, 5 microns. So this is the distribution of diameters. The mean diameter in all cases is the same, 12 micrometers. And then we plot the data. So here we are plotting the results of the simulations. This is the log of 1 minus the probability of failure to the minus 1. And this is how we plot wobble data. And I'm going to show you here in a minute how we come about this. And here we plot the logarithm of the strength. And what we have here are 5 different distributions, okay? Each distribution is associated with a different value of the standard deviation for the distribution of fiber diameters. Now, if you see all of them converge at this point. But what we find is that as the standard deviation in the distribution of diameters increases, see what happens to the distribution. The distribution of a strength that we will calculate using the old standard becomes broader, okay? As we have a more narrow distribution of diameters, the distribution of the strength that we'll calculate becomes more narrow. And this is a way in which we can show the results by normalizing the Weibull modulus that we will calculate if we were to use the old standard versus the true Weibull modulus. And you can see the significant differences. In fact, in some cases, we can underestimate this by 90%, okay? So this is a problem. When you have that much variability in results, this is no longer acceptable. And we did the same for the characteristic strength that you will predict by using the old standard. In this case, you have a factor of 2, which is also unacceptable. So the moral of this exercise is that the old way of calculating the strength of fibers was not correct. And this is a problem when you have a broad distribution of fiber diameters. If all the fibers have the same diameter, that's okay. But if you have a broad distribution of fiber diameters, then the parameters of the distribution of the strengths for the fibers becomes farther and farther from the truth. The rule of thumb is that you have to measure the cross-sectional area of each fiber that you test. If you don't do it, then the errors that you incur either on the Weibull modulus or in the characteristic strength can be very significant. So we proved the hypothesis that it was true. The way of calculating the distribution of the strength according to the old standard was incorrect. The rule of thumb is you have to measure the cross-sectional area of every fiber in your distribution, okay? It's going to take some time, but there's just no question about it. You have to do it, otherwise you're going to have some significant errors. And this is very simple to rationalize. For example, if you have large diameter fibers, usually it takes large breaking loads for large diameter fibers. If you have a small diameter fibers, they usually break with smaller breaking loads. So when you start combining big fibers with small fibers and breaking them with a distribution of loads, you're going to have a lot of scatter. And the conclusion of this is that you cannot calculate the strength of individual fibers using the average cross-sectional areas of the fibers. You cannot do it. The error is way too big. You literally have to go and measure the cross-sectional area of each fiber. Otherwise, the error in the distribution of the strength is going to be very large. Okay? And as a result of that, we wrote a new standard that's C1557. And that standard pretty much describes what I just showed you. It tells you how to test fibers. For example, we use an approach where you take single fibers, you mount them in these pieces of cardboard. They get mounted into a machine. Before you do the test, you can cut the cardboard You can pull the fiber. This is a low displacement curve for a single fiber. You see how they break? Just like we had discussed. Okay? You can calculate the modulus from those displacement curves if you can correct for the machine compliance. You can get the modulus from that analysis. And something that is very important is that you really have to analyze the fracture surface of fibers, especially for ceramics. In fact, using fracture mechanics, if you measure the size of these microstructural features, you can actually estimate the strength of the fibers using Griffith's theory. If you know the fracture toughness of the fibers, you measure the size of the defect, you can find the strength of the fibers. Okay? Any questions? No? Now let me let's go back here for a minute because we're going to do another exercise with Weibull. Let's take a look at that plot. Let's see where that plot comes from. If you're going to be analyzing data using Weibull distribution, you're going to have to do the following. So, according to Weibull distribution, the probability of failure is going to be equal to 1 minus the exponential of minus okay? So let's rewrite this. So this can be right 1 minus probability of failure okay? So let's take natural logarithms. So we get okay? So how do we take care of this negative sign? Okay? So if we take logarithms again, we get okay? So you can have, so if you plot over there, in the vertical axis, double logarithm of 1 over 1 minus PF, okay? And then on the horizontal axis, you plot the logarithm of the stress. What do you get at the slope of these curves? What's the slope of those curves? M, okay? So if you are going to be analyzing data where you take, let's say you take 100 fibers and you pull your fibers, okay? And you organize your fibers in this way, you can find Weibull modulus by plotting the data in that form. And the slope of those curves is going to give you the characteristic strength. And then you can also find, Weibull modulus, and then you can find your characteristic strength once you know your Weibull modulus, okay? So this is a standard way in which we characterize Weibull data. Now, if you remember the discussion, when we started the discussion this morning, we were talking about the size of the sample. You know, if you have 5 fibers, you're not going to get good data. You probably need at least 30 good tests to get a good estimate of the parameters of the distribution. The greater the sample size, the better the confidence that you're going to get on the estimates of your parameters of the distribution, okay? So if you read the standard, one of the things that we recommend in this standard is that you should test at least 30 good fibers to get the data. Okay, let's do one more thing before we break. So I got this from a paper. This is somebody's paper. And you know, you have the double log of 1 over 1 minus PF right here, okay? And then you have the log of the strength. And now you have all the data. So what they did is they did a linear regression, and they get this line. So they get the slope of this line, and they get the wobble modulus, okay? So let me ask you, is this a good fit? What's your opinion? Would you guys say this is a good fit or a bad fit? You see all that curvature? And then you draw a line. Is that good or bad? Yeah, it's not very good. And you know, the problem is that a lot of people, I mean, if you survey the literature, there is a lot of this. There is a lot of this, okay? And sometimes people say, okay. So the next time you do an analysis of a wobble plot, if you see something like this, be suspicious, okay? Be suspicious because there's probably a little glitch there. And the sad part is that lots of papers get published. I mean, lots of papers get published, and this person drew a straight line there to get the wobble modulus. So let me do a little exercise, and I'm going to show you why, when you see these type of things, you have to be suspicious, okay? So we talk about Weibel, Swedish engineer, okay? And you're going to, if you do work in this area, this is one of the names that you're going to hear mentioned the most. We talk about his paper, historical paper. In fact, I strongly encourage you to read that paper. I mean, I know we don't have homeworks in this course, but if I were to give you homework, I will ask you to read that paper. It's a beautiful paper. So next time you grab a cup of coffee, go to the library, get that paper and read it. You're really going to enjoy it. As structural engineers, you guys have to read this paper. It's a beautiful paper. And we talk about the fact that there are no fundamental reasons for why this distribution has to be used, other than it's a very simple distribution to use. Mathematically, it's very simple to handle, and it does a very good job, okay? I mean, it really boils down to that. We talk about how he used it in biology, looking at the fatigue of steels, the strength of steels, the strength of cotton fibers. I show you how we've used it to look at the strength of carbon fibers. I mean, it has multiple applications. So we go back to our friends here, and then they look at the regression. So say, okay, the wobble modulus is going to be 7 because that's the slope of this line. So this is important because we talk about size effects in ceramics, and we talk about the weakest link, okay? And the strength of ceramics is always going to be controlled by a defect, okay? Can be a little pore, can be a crack, can be an inclusion. Anything that becomes a stress concentration in a material is really going to induce a concentrated stress, and that's going to limit the strength of the material, okay? And that's why we talk about flow populations. And these flow populations are usually the result of the way you make the material. If you have a lot of impurities in your material, you're probably going to have inclusions. And if those inclusions are big, they're going to become strength controlling flow. Okay? The material is going to fail at the location of these big inclusions. You could have cracks on the surface, and those cracks can become strength controlling flows. If you remember the last video of the carbon fibers, there was something called sizing. I don't know if you saw it, okay? Sizing is a very thin coating that gets applied to the fibers, and it's applied to protect the fibers during handling, If you don't put a sizing coating on the fibers, it will be very easy to damage the fibers. Even just by touching them with your fingers, you could modify the strength of the fiber. Okay? So that's why they apply this sizing coating to protect the fibers. And this is important because ceramics are going to be very sensitive to flows. So let's do a little exercise, okay? We're going to have a type of fiber, we're going to call it the blue fiber, okay? And this blue fiber is going to have a type of flow, we're going to call it flow type A. It can be a crack on the surface, could be a pore on the surface, but it's going to be always the same on the fiber, okay? And that's going to be a strength limiting flow. So these are our blue fibers. And we're going to assume that the strength distribution of these blue fibers follows Weibel's distribution. And I just show you what that means, okay? So if you take 100 blue fibers and you test them, you're going to have a Weibel distribution that describes the distribution of strengths. And to distinguish it, we're going to call this probability of failure for fiber type A. This is the Weibel modulus for the fiber type A, characteristic strength for the fiber type A. And again, for the Weibel distribution, we have two parameters, Weibel modulus and characteristic strength. So if I test a bunch of blue fibers, this is what I'm going to get. You see how straight this is? Okay? This is a perfect line. If you get the slope of this, you get this value of 15. You can calculate the characteristic strength. In this case, it's going to be equal to 2. And here we have tested 50 fibers. Okay? So these are the blue fibers. Blue fibers have Weibel modulus of 15, characteristic strength of 2, can be 2 megapascals to GPa. And we have a sample size of 50 to get good estimates of the parameters. And as we discussed, we present the data as the double logarithm of 1 minus p to the minus 1 versus the natural log of the stress. Okay? That's how we present Weibel data. Now we have the orange fibers. Okay? We're going to call orange fibers fibers type B. And these fibers have a strength controlling flow. It's a different strength controlling flow. So if the strength controlling flow for fibers A was a pore, we're going to say that the strength controlling flow for the orange fiber is going to be a crack. Okay? It's going to be different. But all the orange fibers are going to break because of this flow. It can be a small crack or a big crack depending on the fiber, but it's the same strength controlling flow. And we assume that the strength of these fibers are distributed according to a Weibel distribution. And then the parameters are going to be MB and sigma sub 0B. And if we go to the instrument machine and we test 50 orange fibers, this is what we get. It's going to be a perfect line. You look at the slope, you get a value of 7 for Weibel modulus. Then you have a characteristic strength. So these fibers are a little bit stronger than the blue fibers. The Weibel modulus here is 7. And then we had a sample size of 50. So this is what happened with the Weibel distribution. See how you have 1 or 2 outliers here. Most of the data are here. But this is what we call extreme value distributions. It's really the weakest values in the distribution, those that are going to control the overall behavior of the system. Okay? And this is characteristic of the Weibel distribution. It's an extreme value distribution. So now we're going to plot the strength distribution for the blue fibers. The modulus is 15, which means that this line is steeper than this line. The modulus here is 7. The characteristic strength is only 2. The characteristic strength is 4. So blue fibers, okay, the distribution is more narrow. Orange fibers, the distribution is more broad. On average, orange fibers are stronger than blue fibers. Okay? Any questions up to this point? So those are blue fibers, orange fibers. They have one type of strength controlling flow, a different type of strength controlling flow. So now I'm going to go to the laboratory, and I'm going to open up a box that has blue fibers. And then I'm going to open up the box that has orange fibers, and I'm going to mix them up. And I'm going to put a third box, and I'm going to get blue fibers, orange fibers, and I'm going to check it, and I'm going to mix it. Then I'm going to go back to the instrument machine, and I'm going to test those fibers. So now the total number of fibers is going to be the sum of the number of fibers of type A plus the number of fibers of type B, okay? And I can divide by n, so I have that the volume fraction of A plus the volume fraction of B has to be equal to 1. And then you can calculate the probability of failure for this array as the product of the volume fraction of A times the probability of failure of A plus the volume fraction of fibers of type B times its probability of failure. And you can rewrite this according to this expression, okay? That's how you calculate the probability of failure of a system that has different types of components. And then I'm going to go to the lab and I'm going to pull my fibers. From the third box, I have blue and orange, okay? And I'm going to pick them up randomly, and I'm going to test them. And what I get is the black, okay? So this black distribution is the result of testing fibers from this third box. And that third box contains both blue fibers and orange fibers. But you see how this distribution is no longer a straight line? Now, if I did what the other author did, I could try to draw a straight line and try to get a slope, but it really doesn't mean anything, okay? It really doesn't mean anything. What I'm looking at is a fairly complex process that is a result of two different distributions. So the message that we get from here is that when you test fibers, you really have to do fractography. And fractography means you take your broken piece and you take it to the scanning electron microscope. And you analyze the cross-sectional area to see what type of defect was responsible for the failure of your fiber, okay? I know it's a lot of work, but unless you do that, you will tend to do this. And you see the curvature here? I bet when this person or these people tested those fibers failed by different ways. Some fibers have something on the surface. And let me show you an example of some typical fractography for fibers. You see this? So you could have crack initiation in this location, okay? You could have internal defect in this location. You could have a big pore. And when I talk about type A and type B, you know, this could be a type A defect close to the surface. You could have here a type B defect, which is a big pore inside the fiber. And when you do the wobble analysis, you really have to separate the type of defect, all the defects that are type A, all the defects type B, and that's the only way you can analyze your data. And this is very important because if you're going to be making predictions, you need to know the parameters of these distributions fairly well. And you have to have good confidence on the meaning of the values that you have. Whether it's a strength, if you're going to be designing a component for a gas turbine that's going to be rotating at 100,000 RPMs at 1400 degrees C, and you want to predict that that's not going to fail because you have 100 passengers in an airplane, you better understand why these materials are failing and that the mathematical expressions that they're using to describe the strength of these materials are appropriate. Okay? Any questions? No? Was that clear? Very good. So let's take a break, and we'll finish composites, talk about some wind energy and how we use these composites to make turbine blades. Okay? Okay.